Hello everyone, this is Anuj. Today we are presenting our senior capstone project, an AI-assisted audio transcription and summarization system. This project focuses on converting recordings into structured, searchable text entirely offline. Audio content like lectures, meetings, and interviews is everywhere today. However, reviewing long recordings is time-consuming. Many existing tools rely on cloud processing, which raises privacy concerns and requires internet access. The main problem we identified are long recordings are difficult to search, manual note-taking is inefficient, and cloud-based tools may expose sensitive data. So we wanted a solution that addresses all these three problems. Our solution is a fully local desktop application that takes audio or video files and converts them into transcripts and summaries. Everything runs offline, so user data never leaves the system.
Hi, this is Sahil, and for this slide, we're going to talk about the main features of our system. The first feature is speech to text transcription. This converts spoken audio into readable text using AI-powered speech recognition technology. This allows users to quickly generate transcripts from lectures, meetings, or interviews. Another key feature is speaker diarization. This helps identify and separate different speakers within the audio, making conversations easier to follow and organize. We also implemented AI-generated summaries, which analyze the transcript and produce concise summaries that highlight the most important information. This helps users save time when reviewing long recordings. And in addition to that, the system includes search and playback functionalities. Users can search for keywords within transcripts and quickly navigate to important sections of the audio. We also added export functionalities, which allows users to save transcripts and summaries for future reference or sharing. And so together, these features create a more efficient and user-friendly way to process and understand audio content. This is Sahil, and this slide explains the overall architecture and workflow of our system. The process begins with audio input, where users upload or record audio files into the application. After the audio is received, the system performs pre-processing. This step prepares the audio for transcription by improving compatibility and helping ensure better speech recognition accuracy. The audio is then sent through the transcription stage, where a speech-to-text model converts spoken language into readable text. Once the transcript is generated, the system performs speaker diarization, which helps separate and identify different speakers within the conversation. This makes multi-speaker recording easier to follow and understand. After diarization, the transcript is processed by the summarization component, which uses AI to generate concise summaries highlighting the key information from the recording. Finally, the results are displayed in the user interface, where users can review transcripts, search content, and interact with the generated summaries. This architecture allows the system to efficiently transform raw audio into organized and useful information. Hi, this is Sahil. This slide shows the step-by-step processing pipeline used in our system. The process begins when the user selects an audio file to upload into the application. This serves as the input for the entire workflow. After the file is uploaded, the system converts the audio into WAV format. This conversion step improves compatibility and ensures the audio can be processed correctly by the transcription model. Next, the transcription process is executed. During this stage, the speech-to-text model analyzes the audio and converts spoken language into readable text. Once the transcript is generated, the system performs speaker identification, also known as speaker diarization. This helps separate and identify different speakers within the recording, making conversations easier to understand and organize. After identifying the speaker, the system generates an AI-based summary from the transcript. The goal of this step is to reduce long recordings to shorter and more concise key points. Finally, the completed transcript and summary are displayed to the user through the interface, where the results can be reviewed, searched, and exported if needed. This pipeline allows the system to efficiently transform raw audio into structured and useful information. This is Sahil, and this slide highlights the main technologies used to develop our system. The primary programming language we used in this project is Python because of its strong support for artificial intelligence, audio processing, and machine learning libraries. We also used PySide-6 to help develop the graphical user interface, allowing users to interact with the system in a more intuitive and user-friendly way. For speech-to-text transcription, we used Faster Whisper, which is an optimized implementation of OpenAI's Whisper model. This helps improve transcription speed and efficiency while maintaining strong accuracy. Another important technology is Pyanote Audio, which we used for speaker diarization. This allows the system to identify and separate multiple speakers within a recording. We also used Llama CPP for local AI-based summarization. This helps generate concise summaries from transcripts while reducing dependency on cloud-based processing. And lastly, we used SQLite, which is used for lightweight local data storage, allowing transcripts and summaries to be stored and managed efficiently within the application. So all of these together, these technologies provide the foundation for building an efficient AI-powered audio transcription and summarization system.
Hello, this is Zach Answer. I'm here to talk to you about the user interface. We are utilizing a PySide-6 interface, which provides file selection, settings management, progress reporting, transcript display, summary display, transcript search, word highlighting, audio playback, click to seek, transcript audio synchronization, and export buttons. The UI communicates with long-running processing through the Qt signals from a background worker thread. More directly, our user interface is broken up into four main sections. On the left-hand side, we have the transcript panel, where the finished transcripts are viewable to the user. This is where you can do things like search and highlight for different words or phrases in the transcript. You can click on different sections of the transcript to sync up the audio and play back the audio starting from that part of the transcript, and as it plays we'll continue highlighting the relevant parts of the transcript that are being read. On the right hand side we have the summary panel. So after the transcript is generated and it generates the summary, this is where this lives. It'll contain a short bulleted list of the main points of the audio file that was transcribed, and then a quick little paragraph summarizing the audio file. We also have on the bottom of the screen the audio playback controls. This controls things like play, stop, pause, and seeking through the audio file. And then we also have our exports features on the bottom, so you can export the transcript, or you can export the summary. This is handy, so if you want to have like the transcript to print out, you can export, print it out. You can export it as like an SRT, like a subtitles, which is nice, like for maybe you're uploading a video, and it gives you an easy way to generate subtitles for the video. We also have on our user interface our settings dialog, where you can change all of your and update all your settings, like for the live transcription, what microphone you want to use if you don't want to use the system default microphone. Controlling things like if your computer supports it, the CUDA acceleration for NVIDIA GPUs that support it, or Apple Silicon acceleration for if you have any Apple like maybe Mac OS devices that support the silicone chips that support this type of acceleration, instead of using CPU, which is it's a little slower for transcribing and summarizing than getting some of the nice improvements you get by being able to do specific accelerations. Yeah, so that's our user interface. Hi, Zach Answer here again to kind of run you through our testing. So our testing focused on verifying that the full local pipeline operates correctly from media selection through exported artifacts. The implementation was tested incrementally, while features were added, including transcription, diarization, summarization, search, playback, click to seek, and transcript synchronization of the audio files. The CUDA and Apple Silicon hardware acceleration, things like our llama.cpp summarization configuration. So here are some of the important tests that we ran. For like file selection. So our file selection is implemented through a queue file dialog. We want to make sure that the user, when they select a supported audio video piece of media file, that it gets loaded into the app correctly, that it doesn't let users import anything that's not supported. So we had to verify that this was working for all supported file types. We use FFmpeg for conversion because our models, particularly our faster whisper model, it works better. It prefers to have the audio file in like a 16 kilohertz mono wave file. So we don't want stereo or maybe some kind of surround sound like a DTS or like maybe like Dolby Atmos or something, like, depending on what the user is trying to convert, transcribe. So we had to make sure FFmpeg was actually converting the user selected files into the appropriate format, and make sure that worked for every supported file type. For our whisper transcription, we implemented through faster whisper. So the way we implemented that is that the transcripts gets chunked into segments that slightly overlap, and to help when it stitches those all back together to form the transcript, to form it back together in a way that makes it easier and makes sense for the user to read. So making sure that text doesn't get cut off for a new line in the middle of a word, or at a weird part of a sentence, or in the middle of a thought. So we had to make sure that was working. This is actually something we had our first major road bump when we were trying to test this. We were getting a lot of malformed JSON objects back that didn't quite follow the JSON structure that we were expecting, that we wanted. So we just decided on using a GBNF grammar syntax to strictly force the JSON objects to be created and created into this strict syntax that didn't allow any malformed or unexpected JSON objects to be made. And the reason why this matters is because before that, if we got a JSON object returned for a part of the transcript that wasn't matching exactly what we were looking for, we would get a lot of bad artifacting characters. We didn't want gibberish in the transcript, and so this that helped fix it, and we were able to verify it was working after that. Things like the hardware acceleration for the CUDA and Apple Silicon for the Whisper, making sure that number one, we had to make sure that when the user checked those settings, that it actually enabled it for their system, making sure that it wouldn't enable and be run if the user's specific hardware didn't actually meet the requirements for that kind of acceleration. Things like the diarization, we have that implemented through a piano runner sub-process in a separate environment. And this is because the piano and the ArcFaster Whisper, they have conflicting dependencies. So we had to branch it off in its own environment to run as a sub-process away from the main app environment. But so we had to make sure, verify that the diarization was working with lots of different types of audio files with different levels of number of speakers, people talking over each other, that kind of thing. So these are just kind of the things we had to worry about when we were going through our testing. That's not even to mention the things we had to do for our test summarization models and the implementation, and things like the audio playback and export and searching and highlighting, our bootstrap scripts to make sure that when the user downloads the app for the first time, and every time they start up, it automatically downloads any missing dependencies, binaries, or models, or anything they might be missing, so that way the user doesn't have to go track down those things on their own, or have something fail because they don't have something. So that's kind of our testing process. Hello, Zach Ganser here again to run you through our final project demonstration. So I have loaded up here our app. You'll see on our main UI, we have a couple of things we can do. We support live transcription as well as selecting a media file to transcribe. I'll run you through some of the settings first. Here we have things like, so we have bundled with it the small Whisper model, but say you want to download one of the larger Whisper models to run, this is what our transcription runs on. You can do that, and then you can set the path for your module to use instead of the default. You can do things like set your language. That way, when the transcription runs, it will know what language you're speaking to help the transcription run. This, for the device and compute type, this handles our hardware acceleration for if your computer supports, like if you have an NVIDIA graphics card that supports the CUDA acceleration, or if you have a Mac that has an Apple Silicon chip that supports Apple Silicon acceleration, you can set here. It's set to auto by default. So if your hardware supports either one of those, it'll run everything using that, because it's much faster than running everything, all the models through your CPU. But say for some reason you don't want to use that, you can go drop down and select CPU if you want. For the live transcription, you can select your microphone input. So it defaults to using the system default microphone, but if you have a specific microphone you want to use, you can switch your input for that as well. We have things like, so our summarization model, so we have packaged it with a fairly robust model that still fits nicely with our fully offline implementation like we wanted. So we're a little conservative on what kind of size model we use for the summarization. But say you have much more space or a much more beefy um, machine. You can go out and you can grab whatever model you want to use for summarization, and you can put the model path in here, and the app will use that instead of the one that comes packaged with it. You enable your speaker diarization here, and that kind of stuff. So let's start off by we'll show off the we'll pick an audio file here, just a MP3, to show off transcribing with a user selected file. So we choose the file here. You can see here we support pretty much every major media file type that you might want to use, other than maybe like MKVs. But then you set that, you just transcribe and summarize. So my computer supports the NVIDIA CUDA acceleration, so this should go fairly fast. First, it's going to run through the audio or video file you uploaded and build the transcription. After that, it's going to, if you have it like I have it selected, run through the diarization, which is where it's going to add speaker labels to stocking, and then it's going to chunk and summarize the transcript. The reason why we're chunking the transcripts is because we're not running on like cloud architecture like a web app or something like that, and this is fully offline. We need to be mindful of the end user's resources available to them, and if we just send the entire transcript to the summarization model, and it is a very large transcript, like say you recorded like a 3-hour class for school, that could just completely eat up all of the resources the user's machine has available, and just everything will grind to a halt. So we chunk it to manageable chunks, and then once all those chunks are put into the summary, so the summary will take the chunks, make a list of bullet points of everything that is important for that chunk. It will combine those bullet point lists together, and then feed that through the summarization model again to get our final summary. And we have it constrained to where we get an output of a list of like maybe like five to eight different bullet points of all the most relevant information from the transcript, and then a brief 1-paragraph summary of the entire transcript. So you can see here this job finished running. We have our transcript on the left-hand side. This file only has one speaker, so there's only speaker A, but another file might have 2 or 3 or 4 mini speakers, and they will all be in here labeled separately. So you can actually see here we can start play back the audio file.
This modern world of science and invention,
so it'll play it back to audio file. It'll highlight the section it's currently doing playback for. You can seek directly in the transcript. If you click here, it'll now start playing from not only has applied science here. You can pause it. You can stop it. You can also you can export your transcript. Let's see. Pull that up real quick. So you can see here we've exported the transcript as a text file. You can also export it as like an SRT. You can export your summary in the same way. Up here, you can search. You can search for, let's search for. I've seen obviously in there, so you can search for that. Let's search something that maybe has some more. There's a lot of these, and you can go previous and next through every mention of that phrase or word. Now I'll demonstrate our live transcription. So I'm going to do this. I'm going to start a live transcription. It started. I'm going to begin talking. So what it will work, how it will work is every 5 seconds, it'll update the transcript with what I was saying. Um, as you can see now, every 5 seconds, the transcript gets updated with what I'm saying. Um, we can pause the live transcription, and it won't transcribe any of these things that I'm saying right now. In case you need to pause to you have to run and go do something, or you get a phone call, or you need to go to the restroom or something, and then you come back to live transcription. You can click to resume, and then as you'll see now, it's going to start transcribing again. And so once you're done with your transcript, you do stop live. You press the stop live button here, and then it's gonna take that transcript and it's gonna summarize it for you. Um, where did it go? Ah, okay, so it's gonna take that transcript and it's gonna summarize it for you. Um, we'll just generate a little bit more of the live transcript again. Um, okay, and we'll stop it here and we'll show you the summarization. And so it's going to combine the chunk summary then, and you're gonna get a summary. And the same thing with the live transcription. You can export the transcript or export the summary. Um, and yeah, I think this is a really handy app. Most live transcription and or like audio transcription apps we saw were online based, and we thought maybe there's a market here for users who are probably maybe more privacy focused and concerned about security. They don't want to feed their data to something that's on the cloud or online, and so this kind of is a nice little app for anybody who's concerned about those kind of issues.
Hello, my name is Hoida. Through this project, we learn how to integrate multiple AI technology into one complete application. We worked with speech to text transcription, speaking, diarization, and local AI summarization model, which give us hand-on experience with a real-world AI system. One major thing we learned was how important it is to manage reliance and optimize performance, especially when supporting both CPU and GPU acceleration. We also learn how to design a responsive user interface that keeps the application smooth while processing a large audio file. One of the biggest challenges we faced was dealing with dependency conflicts between different library and framework. We also had to spend time configuring models correctly and improving performance for different hardware environments. Even through these challenges were difficult, but they help us better understanding software, integrate, and troubleshooting. For future work, we would like to add features such as patch processing, uh, editable transcript, subtitle export, and transcript-based question answering. These additional would make the application more flexible and useful for users in both academic and professional settings. In conclusion, our project provide a privacy-focused and fully offline solution for audio transcription and summarization. It allows users to review recording more efficiently without relying on cloud services. Overall, this project gave us valuable experience in AI development, software engineering, and teamwork.